Hello everyone and welcome to this lecture on Kubernetes Jobs. So introduction to Kubernetes Jobs. A job in Kubernetes is a controller object that represents a finite tasks. It creates one or more pods and ensures that a specified number of them successfully terminate. As pod complete, the job tracks these successful completions. When a job is deleted, it cleans up the pods it created. If a job is suspended, it will delete its active pods until the job is resumed. So this is the very high level diagram. So job basically is a controller object which creates one or more pods, and the job will track the successful completions of those pods. And once it's completed, it will clean up the pods when a job is deleted. Or you also can suspend, which will delete active jobs when the job is suspended. So running a job object is created to ensure that one pod runs to completion. If the first pod fails or is deleted, the job will start a new pod. A job can also be used to run multiple pods in parallel. If you want to run a job on a schedule, you can use a cron job. So just to differentiate, so job is basically you will run one-time tasks which must run to completion. So you have deployments, you have stateful sets, and you have daemon sets. But those are for long-running jobs which are always there. They are not, so just think of them as long-running applications. So they must be running all the time, and they have some specific use cases. So deployment, you can just think of as a web application. Stateful sets, you can just think of applications like databases. You can run MySQL, Cassandra, Kafka cluster. So it's always there. And then you have daemon set, which is some application which must run on each node. But job is like one-time job. You can run it just think of a batch job. So you have data analytics or machine learning job. So if it is just one-time activity, you trigger a job, it will run, it will log the output and the result. You can monitor it, and once it's done, it's done. So just think of it that. And you have cron job, which is basically run on a schedule. So it's slightly different, but the main key takeaway is job. So anytime in Kubernetes you have to run something one-off or one time, you will be using a job. So you have job object which creates pod. For example, if there is only one pod required, it will create one. But if it's parallel or if it's sequential, you can specify. So create this particular pod. If it fails, then pod 2 will be created for parallel execution, and then you can have parallel pods. So it depends on the job configuration. So here is an example of example job, and it computes pi to 2000 decimal places, and it prints the result, and it takes around 10 seconds to complete. So this is a code. So we have got a container, and there's a Perl container which we can use, and we can just run this particular command, Perl mbignum and bpi and wle. So this is very specific, but this is just an example of a job, because this we need to run only once. So just think of some scientific and data analytical job. So you can, so this example clearly illustrate what we should use job and under what situations. So once if you from this YAML, if you do kubectl apply, this is how you can do kubectl describe job and the job name. So it will have all the information, the parallelism, completions. So we haven't specified all those values. So that's why the default value is 1 start time, end time. And you have got, so it will also show you the pod. So this job name is pi, and so pod will have job name dash, and there will be some randomly allocated value of the pod that it has created, and it will log its output also. So if you do kubectl logs, the name of jobs.py, you will see the output. You can also do kubectl logs pod.pod name. So you can take the pod name, in this case pi-xf9p4, and if you do kubectl logs pod, the name of the pod, you will see the similar output. Okay, writing a job spec. So a job spec requires API version, kind, and metadata, which we have seen. The metadata.name of the job is used as part of the basis for naming the pods it creates. So that we have seen in case of pi, we have pi dash, some randomly generated phi later mixture of alphanumeric code. And the job spec also requires a spec section, which we have seen. And the spec.template is a pod template. So just remember this. After spec.template, whatever you see is exactly as a pod template, and it has the same schema as a pod, except it is nested. So this is the only thing, and does not have an API version or kind. So they are parallel execution for jobs. So you have non-parallel jobs. So normally only one pod is started unless pod fails. The job is complete as soon as pod terminates successfully. Then we have parallel jobs with fixed completion count. So specify a non-zero positive value for spec completions. The job represents the overall task and it's complete when there are spec.completion successful pods. And when using spec.completion mode equal to indexed, each pod gets a different index in the range of 0 to spec.completions -1. So there are total, there's a field called spec.completions. So you can specify some value. For example, if it's 4 or 5, sorry, then it will go from 0, 1, 2, 3, 4, -1, total -1. And then we have parallel jobs with work queue. So do not specify spec.completions, default to spec.parallelism. And the pods must coordinate amongst themselves or an external service to determine what each should work on. Each pod is independently capable of determining whether or not all its peers are done, and thus the entire job is done. When any pod from job terminates with success, no new pods are created. Once at least one pod is terminated with success, all pods are terminated. Then the job is completed with success. And 6, once any pod has exited with success, no other pod should still be doing any work for this task or writing any output. They should all be in the process of exiting. Okay, next we'll see some job completion modes in Kubernetes. So in Kubernetes, jobs with a fixed completion count can specify a completion mode in spec.completion mode. So there is a field called spec.completion mode, and it has got some values. So one is non-indexed, which is the default, and complete when spec.completions mode have successfully completed. So this is since this is default, you can just specify spec.completion. So non-indexed is the default mode. In this mode, the job is considered complete when there have been .spec.completions successfully. So if you specify, there should be 5 total completions. So when there have been .spec.completions successfully completed pods, each pod completion is similar to each other. Jobs with null value in spec.completions are implicitly non-indexed. So this is the default, and if you don't specify any value which that is null, it automatically becomes non-indexed. And then we have indexed. So in indexed mode, the pods of a job receive an associated completion index from 0 to total of spec.completions -1. So if you have 5 in spec.completions, it will be 0, 1, 2, 3, 4 up to last -1. And this index can be accessed through various means, and those means are, there is the pod annotation as part of pod host name, or from the environment variable. There is a variable called job completion job_completion index within the containerized task. Okay, handling index duplications in indexed mode. So we are just continuing from indexed mode. So how to handle duplications in indexed mode? The pod is considered complete when there is one successful completed pod for each index. This mode is used for parallel processing with static work assignment. It is rare, but due to reasons like node failures, kubelet restarts, or pod evictions, more than one pod could start from the same index. In case of index duplication, only the first pod that completes successfully count towards the completion count and updates the job status. Any other pods that are running or have completed for the same index will be deleted by the job controller once they are detected. Okay, next is handling pod and container failures. A container in a pod may fail due to several reasons such as non-zero exit code or exceeding a memory limit, etc. Okay, if spec.template.spec.restart policy equal to failure, then the pod stays on the node, but the container is restarted. Hence, the program must handle restart policy or specify the restart policy as never. An entire pod can fail for reasons such as the pod being removed from the node or a container of the pod failing with restart policy equal to never. When this happens, the job controller starts a new pod. Hence, the application must be able to handle being restarted in a new pod. By default, each pod failure is counted towards the spec.backoff limit. So there is some within a job there is a backoff limit, and each pod failure will count toward the backoff limit. This behavior can be customized by setting the job pod failure policy. There is something called job pod failure policy also. So there is a failure and backoff limit is incremented, and there is something called job pod failure policy that can handle that can actually customize this particular behavior. We'll see that. Okay, if spec.parallelism and spec.completions are both set to be greater than 1, then multiple pods may be running at once. Hence, the pods must be tolerant of concurrency. Okay, pod backoff failure policy. So this is from previous slide. So this is how. So I'll try to explain. The pod backoff failure policy is designed to manage situations where a job needs to fail after a certain number of retries due to a logical error such as a configuration issue. So this .spec.backoff limit. Okay, so this is achieved by setting. So the pod backoff failure policy aids in managing logical error. So now this is achieved by setting spec.backoff limit to specify the number of retries before considering a job as failed. So by default, the backoff limit is set to 6. So this, if you don't specify that there is a limit, is 6, and with failed pods being recreated by the job controller. So every time there is a failure, it will recreate those pods with an exponential backoff delay. So this exponential backoff delay is 10 seconds, then it becomes 20 seconds, 40 seconds, 80 seconds, and final last there is a cap of 6 minutes. The job is considered failed if the number of retries reaches reaches .spec.backoff limit. So let's say the value is 6, which is the default. So let's say you start a job, first pod fail, there will be another which will be started after 10 seconds, then that fails, and after 20 seconds one more starts, then 80 seconds, 40 seconds, 80 seconds, like this it will continue till there are total number of 6 failures. The number of retries is calculated either from the number of pods with spec.status.phase equal to failed. So there is every pod has a status field phase failed, or when using the restart policy on failure. So within the pod you can have restart policy on failure from the so with spec.status being failed, or restart policy on failure from the number of retries in all the containers of the pods with spec.status.phase equal to pending or running. So debugging considerations for pod backoff failure policy. If your job has the restart policy to on failure, note that your pod running the job will be terminated once the backoff limit has been reached. This termination can make the debugging process more difficult as it interrupts the runtime environment and potentially the reproduction of the issue. To ease the debugging process, it is suggested to set the restart policy to never, because if it restarting on failure, it can go into infinite loop, or debugging may become difficult. So it's suggested to reset the restart policy to never during the debugging phase, or utilize a logging system to ensure the output from failed jobs isn't lost inadvertently, and this allows for complete and continuous logging of the jobs process, which aids in understanding the point and the cause of failure. Okay, pod failure policy. The pod failure policy requires the job pod failure policy feature gate to be enabled in your cluster for configuration, and it is also recommended to enable the pod disruption condition feature gate. This will help detect and handle pod disruption conditions in pod failure policy, enhancing the robustness and reliability of your cluster. The pod failure policy, defined with spec.pod failure policy field, is designed to handle pod failures based on a container exit codes and pod conditions, providing a granular control over job failure and recovery scenarios. So, use cases for pod failure policy. Pod failure policy can be utilized to optimize the cost of running workloads by terminating a job as soon as one of its pod fails with an exit code indicating a software bug. Unnecessary pod restarts can be avoided. In situations where it's crucial for a job to finish despite disruptions, the pod failure policy can be set to ignore pod failures caused by disruptions like preemption, API initiated eviction, or taint based eviction, and these disruptions won't count towards the .spec.backoff limit of retries, thereby ensuring job completion. And last point, the pod failure policy can be configured using the spec.pod failure policy field. This policy helps handle pod failures based on the container exit codes and pod conditions, providing a reliable and efficient way to manage workload failures in your cluster. So this is an example of a job which has got pod failure policy. So job looks completely normal, like we rest all field is like we have completion, so there should be 12 completion, and three pods will start in parallel. So we have 3 batches of 3, so 3, 3, 3, 3, and there's a pod template, and you have restart policy equal to never, so it can be on failure or never. Then this is the main container, so this is a bash container, and we are invoking the bash shell, and we are passing the args, and basically it's just echoing hello world and sleep 5 and exit code 42, and backoff limit is 6. So this is a default anyway, and this is a pod failure policy. This part is something which is introduced. So we have got rules. So action on fail job on exit code, container name. So this one must match main. So here main, and this main matches, and this one is saying action to fail this job in this if the exit code. So exit code matches, which is here over here, exit 42, and value. So this is an array, so exit code can be more than one value. So in that case, fail the job. And then you have another which is action ignore on pod conditions disruption target. So if there is any pod disruption because of like API or node failure or something, then it will be ignored. Okay. And now job termination and cleanup. By default, a job will run uninterrupted unless a pod fails, at which point it will try to restart the pod that I've already talked about. And you can set the active deadline seconds to limit the overall time for the job. The job will be active during this time and will be terminated if it exceeds this limit. So basically, active deadline seconds is start once the pod container start, how much time you want to allocate. So basically it's like a timeout. Just think of it as a timeout. That's why the name is active. So from it will start counting when the container starts. So you give it some time, and if for some reason if it doesn't finish in that the deadline, it will be terminated. you can set the spec.ttl seconds after finished to limit the lifetime of a job that has finished execution, and that can be either complete or failed. The job will automatically deleted after the time to live expires. So even the job object will be deleted. You can also manually delete a job. This will also delete all the pods associated with the job. So as I mentioned, when you create a job, you can have a number of completions, parallels. So it will create that many number of pods, and they will stay even after they finish. They will stay just in case you want to check the logs and all. But if you delete the job object, all the associated pods will be automatically deleted because they are tracked using the name of the job, as we have seen. So this is the example of job with timeout. So I'll try to explain. Another way to terminate a job is by setting an active deadline, which we have seen. So in this case, we have given 100 seconds. Do this by setting this particular field of the job to a number of seconds. The active deadline seconds applies to the duration of the job, no matter how many pods are created. So okay, this is the important thing to remember. It applies to the duration of the job, and it does not, no matter how many pods are created. Once a job reaches active deadline seconds, all of its running pods are terminated, and the job status will become type. It can be failed with reason deadline exceeded. So this you will see in the message. And note, there's a note that that spec.active deadline seconds, this particular value takes precedence over spec.backoff limit. So this has higher precedence over backoff limit. So if you specify, by default it's 6, but if you specify some other value, that will have less precedence, and therefore a job that is retrying one or more failed jobs will not deploy additional pods once it reaches the time limit specified by the active deadline seconds. So if you have, for example, backoff limit is 6 and you have given 100, so let's say 1 starts and for some reason it fails, it will try to start one more pod. So it's something like this. You have got first pod starting and it takes, for example, 10 seconds, but after 10 seconds it fails. Then you have one more pod starting and it takes, this one is taking 20 seconds, and then let's say third one is taking 10, 20, and let's say this one is taking 50 seconds. So now 80 seconds have already passed, and now you have got one which is 20 seconds, so now 100. So this has exhausted all the active deadline seconds allocated for this. So once active deadline seconds has come to 100, this will not even though backoff limit is 6, it will not let pod number 5 and 6 to execute because it has reached the active deadline seconds. Okay. And that's all. Thanks for watching.